Unit 1 on Functions, Lesson 3. Today we're going to talk about finding relative min and max values using the graphing calculator. We're going to classify functions as even or odd based on symmetry, and we're going to use the graphing calculator to graph piecewise functions. If you take a look at the polynomial graph shown on the left, you're going to see a bunch of mountains and valleys. We're going to refer to the mountaintops in this diagram as relative maximums. They aren't absolute maximums because there's points that fall higher. However, you'll notice that the graph will rise and then fall on either side of those points. In the valleys or low spots of the graph, we'll refer to this as relative minimums, not the absolute lowest point. However, to the left and to the right, you'll see points that exist higher than the relative minimums. Our first activity is to use the graphing calculator to find all relative mins and maxes of the following. When we enter this into the graphing calculator, this should be the graph that we attain. Notice I've already gone into my calculator, entered the equation, and I'm now going to graph in the standard window setting. So if I click on zoom and choose option 6, I now have the standard window setting. In looking at this graph, it's clear that I have one mountaintop and one valley, neither of which are the absolute top or bottoms of the graph. If we go up here to the top, my relative maximum, I can use the calculator to find the exact point that exists at the top of that mountain. We want the calculator to do some work, so we're going into second trace, and we're going to choose sliding down maximum. Hit enter, and notice the calculator down here is going to ask for the left bound. We need to have the calculator focus on just the mountaintop. So I've moved my cursor to the left of the mountaintop and I'm going to hit enter. Now it asks for the right bound. So I move the cursor to the right of the mountaintop and hit enter. Notice on my screen I have these dotted lines. They're an indicator of how much of the graph is now between those 2 points. That is the only thing the calculator is going to work with. At the bottom it now asks for where we think that the guess of the maximum is. So I'm going to move my cursor to the absolute top and hit enter. Notice the exact value is located here. Please do not estimate, do not use trace. We are having the calculator find the exact point, negative 0.20, 7.22. That would be the location of that shining cursor, which is the maximum. In following the same steps, second trace, we can go in and calculate the minimum point. So notice my minimum is located down here at the bottom in the valley. I'm going to move my cursor over to the left of the valley, hit enter. Then I'm going to move to the right to find the right bound or point to the right of the valley. I then move my cursor to where I think the lowest point is and hit enter. My minimum value is located at 1.09, 3.95. If I go back to my PowerPoint, which mimics the notes, you'll find that these are the 2 points that we just found. Why is this important with what we're going to do now? Well, I'm also going to ask you to find the domain range in increasing or decreasing intervals. So let's start with domain. Domain references the x values, how far left and how far right the graph travels. So if you notice, my graph is going to continue to go down, down, down to the left, and it's going to continue to go up, up, up to the right. So when we say what are the x values for which this is defined, how far left, how far right, the answer is going to be negative infinity to infinity. There are no values that are left out of a table, so all numbers would be included in the x values of a table. If we talk about the range is how far south and how far north. Well, from south to north, there are no points that are left out. My range is also going to be negative infinity to infinity. The next part of this example is asking you to find the intervals over which the function is increasing or decreasing. Notice how I've highlighted on the graph two yellow sections and a green section. The yellow section is increasing. The green section is decreasing. A couple of things to keep in mind. First of all graphs in math are read left to right, just like the English language. So if you were illustrating using words what's going on, think of a roller coaster. You would be going up, 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 up to the relative max, then you would be going down, 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 down to the relative min, then you would be going up, 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 and climbing again on the second yellow part of the graph. Another thing to consider is that when I ask you for increasing and decreasing intervals, your brain is going to think in terms of y. But we don't care about the y values. We're going to talk about the intervals of x. So if I look at the first yellow section, which runs from here to here, how far left this graph goes is negative infinity. Remember, this is going to continue to go down, 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 and over here. It's going to follow this trajectory. So negative infinity to negative 0.20, because that is the x value, right here, the x value of the relative max. Then notice here's a new symbol for you, which is the union symbol, which is another way of saying, and we have another interval that we need to include. That is going to start here at the bottom, or the relative min value of 1.09, not the y value, the x value. This yellow section over here is going to continue to grow up here to the right. So how far right does the graph go? It's going to go to infinity. This is my increasing intervals. The decreasing intervals are there's only one, which lies in this singular green section. Using the x values from negative 0.20 to 1.09, this is my decreasing part of the graph. Again, you will think in y's, but you can only write down the x values for your intervals. The next topic we want to talk about are even versus odd functions. At the beginning, we often looked at things like the vertical line test, or we would look at whether or not something was a function by looking at a table. We are further going to classify functions once we have said something is a function and say, well, is it an even function, is it an odd function, or is it neither of those? If we look at the definition of even, it's symmetric with the y-axis, not a different axis, not a different vertical line, only the y-axis. By definition at the bottom, f of negative x is equal to f of x. Well, what does that mean? Well, if I look at the 2 points, I could give them values. So for example, look at the table. 1, 2 would be the dot located right here. Negative 1, 2 would be the dot located here. The definition of even says if I take an x value and I change its sign, does y remain the same? If it does, looking at a table, this is the definition of even. Let's compare it to the odd function. The odd function, if we look at this point, has an x value of 1, 3, for example. In order for this to be an odd function, I would need to have negative 1, negative 3. Not only do I have a sign change in x, but then I also have a sign change in y. Graphically, if I draw in the line y equals x, which is this green line, you'll see that if I take the graph, fold it over top of the x-axis, and then again over y, I have a symmetry that exists. It's a double flip symmetry. By definition, we say that this is symmetric to the origin, and that f of negative x is the same thing as negative f of x. So let's look at a couple examples. In example 2, f of x is equal to x cubed minus x. If I substitute 2 into the function, so I find f of 2, I get 6. If I complete the sign change and change the x value of 2 to negative 2 and plug it into the function, I get negative 6. The fact that I have a sign change in x that is mirrored with a sign change in y is the definition of odd. The next example x squared plus 2x minus 1 of this function, if I look at the table, you'll see that I have a sign change, 2 to negative 2, but I don't have a simple sign change in the y's. They don't remain the same either, which means this is an example of neither. It's not a further classification of the function. In example 4, x squared minus 4, this would be an example of an even function. If I graphed it, the y-axis would run through the center of the graph. But if I look at the table and I plug in a number like 3, I get a 5. If I plug in negative 3, the opposite, I also get 5. No sign change indicates that this is even. If you plug in a number to any of these examples and you get 0 for y, 0 has no sign change. So it's not a number that we can use to evaluate whether something is odd or even. My suggestion would be that you redo the table and choose a different number. Notice how in example 4 I went to 3 instead of using 2 and negative 2, which would have yielded 0. That doesn't indicate a sign change. The last topic in this unit is graphing piecewise functions. I wish that I was in class to do this with you. However, we're going to look at these as 3 separate functions that are graphed in the same diagram. The key here is the fact that I can only graph them in certain parts of the coordinate plane. Take a look at the first example. The first piece, x plus 3, is only for x values that are less than or equal to 0. So on my graph, notice I go to an x value of 0, which would be right here, and I drew in this little dotted line. Okay? The fact that x has to be less than 0 means I'm dealing with only this area of the graph. I don't care about anything to the right of the green line, only the left. My suggestion from you there is to make a table. Notice that I have a 0, which is the indicator number from the inequality, and then I chose a number that makes this inequality true. Negative 1 is less than 0. I plug these two numbers into this top function, x plus 3, and I come out with these two outputs. 0 yields a 3, negative 1 yields a 2. Now notice, x is allowed to equal 0, which means when I graph it, it's going to be a solid circle. Negative 1 is less than or equal to 0. This x value makes this inequality true. Therefore, I use a solid dot for the second point as well. I should recognize y equals x plus 3 as a line, so the last thing I need to do is to draw the shape and connect the 2 points. Also notice I did not continue the line into anything to the right region because I'm only allowed to graph to when x is 0. Let's talk about the middle section. The middle section is defined between 0 and 2. Technically, it is not defined at 0 because I don't have an equal sign here, but that's going to become a boundary number. If I read my equation correctly, this says y equals 3. Y equals 3 is a horizontal line. Notice 0 and 2, this middle region for which I'm pointing my cursor at right now, this is the only area in which I can draw this function. Nothing to the right and nothing to the left. I then create a table. I'm going to use the two numbers that they gave me, 0 and 2, and then I know my output is always going to be 3. This is the only tricky part of graphing this section. 0, 3 came from the inequality, 0, 3. However, it is an open circle, not a closed circle because x is not allowed technically to be 0. The 2, however, has an equal sign here, which means x is allowed to be 2. It's part of the domain, and then 3 is going to be my ordered pair. So notice at 0, 3, I use an open circle, but at 2, 3, I use a closed circle. I connect the 2 as it's a horizontal line, and I now have the middle piece of my graph. The last part of my piecewise function is x is greater than 2. So notice I have a dotted line when x is 2. So think about it. X is 0, x is 1, x is 2. This is my boundary line. I can't draw any part of this graph to the left because I'm drawing it greater than 2. And I recognize that this is also a line, 2x minus 1. I'm going to set up a chart. I only have one x value that I'm plugging in, but I'm going to choose another number in this interval. 3 is a convenient number because it's bigger than 2. Take these two x values, plug 2 into 2x minus 1, gives me 3. Plug 3 in, yields 5. I now have 2 ordered pairs. Again, when I plug in the 2, this is not true. 2 is not greater than 2, which means I'm going to need an open circle on the graph. 3 is greater than 2. That is a true inequality, so that means my graph will have a solid line. 2, 3 is here, open circle. 3, 5 is here, closed circle. I recognize this as a line, so I draw in my line. As the final answer to this graph, you should have 3 separate parts: the green section, the blue section, and the red section. I often get questions about, well, what happens when you have an open circle and a closed circle in the same spot? The closed circle overrides the graph of the open circle. This is an example of what we would call a continuous function. We can draw the whole thing without picking up our pencil. And that happens because the closed circles trump the open circles. If you were asked to graph piecewise functions on the calculator, you have to click the mode button on your calculator and change it to dot mode. These would be the commands that you would type into your calculator. The only issue you have with the graphing calculator, it will not tell you if the endpoint of a discontinuous graph is open or closed circle. So there are definitely limitations, and I will tell you on your test, you will not be graphing with the graphing calculator. You will be expected to graph piecewise functions by hand, 3 or 2 separate pieces depending on the problem. Feel free to pause to write down this information. Here's an example for you to try on your own. See if you can do the 3 separate parts. Pause the video because I'm going to bring the answer up next. When you look at the answer key, you can assume that the first function, 3x plus 6, is in red. It has an arrowhead on the far left and continues off of the graph. The parabola x squared minus 8 is in the center section between -3 and 4. And then the third section, the green section, is the line y equals 8, which is a horizontal line. This is an example of a discontinuous graph because of the break between the red and the blue graph. In your packet, you should have 4 problems in a graphing worksheet. In the first problem, it's the exact same picture that you would graph twice. Second problem underneath is the same, etc. I'm going to ask you to highlight where the graph is increasing with a yellow highlighter. Highlight where the graph is decreasing with a green highlighter. Write the intervals in which it is increasing and decreasing. So as I return to the previous topic, we need to evaluate what are we missing in order to write the intervals. Well, the point of the lesson was for us to look at the mins and the maxes. So you're going to need your graphing calculator to go in and calculate the mins and maxes. Left bound, right bound, guess. Left bound, right bound, guess, especially if you have multiple max or mins in the same drawing. These are our first 2 graphs, graphed in the standard window setting. When you plot the lowest point, you will find that the x value is 2, something. You need to mark that point clearly right here. So I would put a dot here. I would put an ordered pair, x, y, using the minimum feature of your calculator. This graph is decreasing from -infinity to 2, and then it increases from 2 to infinity. you look at the next example, we have question marks listed. Why? Well, the window does not allow us to see what the minimum is or where it's located, so you can't have it calculate to find that. You're going to need to zoom out. So go into zoom, zoom out or zoom fit, then go into calculate and choose minimum and find the ordered pair. You'll be able to replace the question marks with the X values that you find of the minimum. The answers to the next two graphs are shown. Your assignment is number